Completing the square can also be used to prove that the vertex of a quadratic equation will always be in the same location, namely, the x value of the vertex will always be at negative b over 2a. Completing the square allows us the strategy necessary so that we can see that as the vertex. And actually, completing the square is the skill that we need to see the connection between the standard form of a quadratic equation, which is what we have here, and the vertex form, which is what you're going to see at the end. Now, the algebra in this example is a little bit trickier and takes a little bit more careful analysis as we walk through the steps. So it's not going to be as easy as just, let's do this, let's do this, let's do this, and poof, out comes the vertex. You want to be very careful about the way that we write this. We want to be very careful about maintaining the equality of the equation, the equalities in the equation as we work down. So the first thing that we're going to do in an effort to get this written in vertex form so we can see that vertex is that we're going to factor an a out of just the first two terms of this expression. So we're going to leave the c alone. So it's going to look like this. We're going to take an a out of the first expression, which is just going to leave an x squared. And then we're going to take an a out of the second expression, which is going to leave b over ax. So if you imagine using the distributive property and sending that a back in, you'd get back to where you started. We're not going to touch the c, and we're going to leave all of that equal to 0. The reason that we're going to do that is because we're going to use this part in here to complete the square. Now, if you watched the quadratic formula video already, you will have seen what that completing the square looks like, but we're going to leave this a, x squared plus b over ax, and we're going to add in an extra term that is the result of dividing this coefficient by 2 and then squaring it, b squared over 4a squared. So that's just completing the square on that inside expression in here. Now, in order to maintain the equality, there's two different things that we could do. We could take that exact same term and add it to the right-hand side of the equation. But for the purposes of this exercise, we're actually going to take a little bit of a different route. We're going to subtract a over b squared minus 4a squared from the left-hand side of the equation. So why can we get away with that? Well, if we have this added on to the left-hand side of the equation here, and that's technically a times that expression, or that term, that part of the expression. If I have this added on to the left-hand side of the equation, and then later on in the equation, I take it away from the left-hand side of the equation, that exact same thing, then I have maintained the equality that I started with. It's just a matter of rewriting it. Is it more complicated than what it was when we started? Absolutely. Does it have a bunch of extra terms that we didn't previously have before? Absolutely. But adding in that term here and then taking it away makes no functional difference to the equation. It's still going to have the same solutions because the thing you added in is then being taken away. So imagine if I was going the opposite direction, the first thing that I would do is get rid of both of those because they are opposites of one another. So if I'm working down, this is merely a mechanism to get this written in a way that allows me to simplify a little bit. And the thing that I care about most is the fact that I have now created a perfect square trinomial in here. So I can say a times x plus b over 2a, all of that squared, plus, and now for the purposes of this exercise, I'm going to just clean this up a little bit because there's no common denominators to have here, plus c minus b squared over 4a. All of that is equal to 0. Now, this should look familiar to you. This is the vertex form. So we have right here what we normally would have called x minus h, and that means that our vertex is going to be in an x-coordinate of negative b over 2a. And over here is the k that we're used to adding because there's no x in there. This is all just a bunch of constants. So that ends up being the y-coordinate of the vertex. We don't memorize this as that expression as the y-coordinate of the vertex because that's a really inefficient expression and you would just be memorizing it for the sake of memorizing it. But the vertex happens so often and maintains such an importance to the graph that we remember that negative b over 2a is its location for the x-coordinate, and that comes from completing the square onto the standard form.